So, magnetic moment of nuclei, and in this extreme single particle model we assume for odd A nuclei that the last unpaired particle decides the magnetic moment, and for that last unpaired particle we have two cases, J is L plus half or J is L minus half, right. If J is L plus half and if I demand that M J should be equal to J, in that state we are working. So, the only possibilities are that M L is equal to L and M S is equal to half. Okay. In that case we discussed, it is simple to calculate that expectation value of mu z. If you calculate expectation value of mu z, and mu z is what? G L L z plus G S S z and mu n over h cross, and this expectation value of mu z is simply G L, and L z is M L times h cross, and M L is L. So, this is L plus G S, S z is plus half. So, it is plus half times mu n, right, simple to calculate. And then if it is proton, if the last unpaired particle is proton, then G L is 1 and how much is G S? 5.5857. Okay. So, you substitute those things and mu z is equal to G L is 1. So, L you can write as J minus half, and then this divided by 2. So, plus 2.7928, which is J plus 2.2928 times mu n. And if that last particle is neutron, in that case G L is 0 and how much is G S? Minus 3.8260. So, mu z is G L is 0 and G S by 2, that is minus 1.9130 mu n. So, that is simple to calculate, but then the other case is a bit more complex, where J is L minus half. So, if J is L minus half, then we said that you can have two possibilities, M J is equal to half is equal to L and M S is equal to minus half, this was one, and the wave function corresponding to this we called it psi 1. Please check, did we call this as psi 1? The other possibility was that M L was L minus 1 and M S was plus half, and we call this psi, right. This is the order, because we are looking at M J equal to J states in which this expectation value has to be taken. So, both possibilities are here. So, psi can be written as A psi 1 plus B psi 2. Then we calculated A and B using one that this is normalized, which gives me mod A square plus mod B square equal to 1, and the other we operated as raising operator and did some calculations, and what we got, mod A square 2L by 2L plus 1 and mod B square 1 by 2L plus 1. We had also calculated that psi 1 mu z psi 1, remember. If this be the case, if the wave function has M L equal to L and M S is equal to minus half, you can just put that here and you can get this will be GL into L. So, ML is equal to L. So, GL into L and plus GS into minus half times mu n, right. And with psi 2 mu z psi 2, this will be GL into L minus half and plus GS into half mu n. And this psi mu z psi, this will be mod A square times this first one, psi 1 mu z psi 1 and plus mod B square times psi 2 mu z psi 2. Okay. All right. So, the net average magnetic moment has to be calculated in this wave function psi, which is A psi 1 plus B psi 2. For pure psi 1, the expectation value would have been this, and for pure psi 2 it would have been this, not L minus half, let it is L minus 1, because that L this ML is L minus 1 here. So, L minus 1 here and this half. So, this half here and this A square plus B square. So, let us calculate this. Psi mu z psi is equal to mod A square, what it is, 2L by 2L plus 1, and psi 1 mu z psi 1. Psi 1 mu z psi 1 is here, GL into L, GL into L plus GS into minus half. This is, we will put mu n, okay, let me put mu n here itself, mu n, and plus mod B square 2L plus 1, then GL L minus 1 and plus GS half mu n. So, take this 1 by 2L plus 1 common, and mu n also we can take common here, and then you have 2L. So, GL and collect all the GL, both GL at one place. So, this I have taken out. So, it is 2L square from here, right, 2L square, and from here I have taken this out plus L minus 1. So, plus L and minus 1 and collect that GS. GS is minus L from here, minus L from here, and GS plus half from there, right. So, let us write it in terms of J, since J is L minus half, L is J plus half. So, in place of L, let us write J plus half. This is mu n divided by L is J plus half. So, 2L is 2J plus 1 and another plus 1. So, it is 2 bracket J plus 1 GL 2L square. So, 2 into J plus half, yes, J plus half square, okay, plus L J plus half and minus 1, okay. All right, check all the algebra by the time I am doing something else. Check all the algebra, is that correct? And possibly go ahead and solve it, make simplify. Do you cancel that constant term? So, this is GL part, okay. Let us write that GS part also. This is minus GS times J, okay. mu n 2 j plus 1 GL j plus half. If you wish, you can take common also, right, or from here I could have taken L common. So, or I can just expand it. If I just expand it, what happens? J square and 2 j square, then this part is plus 2 j and plus 1 by 2 and plus this j, and half minus 1 is minus half and minus gs times j. So, does this cancel? This is what I was telling, that the constant part should cancel out, and now I can take that j common out. So, mu n j 2 j plus 1 GL, hey, stop here, this bracket GL bracket closes here, this bracket closes here, GL into this whole thing. So, GL into this whole thing, and then minus GS into J. Follow the algebra correctly. So, GL into up to this. So, this bracket in fact closes here, minus GSJ, right. So, GL into 2J plus 3 and minus GS times J. J I have taken, all right, very good, very good. Be careful and alert. So, now let us write it for neutron and for proton. Let me write it on the other side of the board. So, I am erasing this portion and see what happens for a proton if the last nucleon is a proton. If that last nucleon is a proton and you are dealing with this case, J is equal to L minus half. So, proton, right. So, that mu z is equal to J, mu n will be anyway there. So, J over 2 J plus 1. Now, GL is 1. So, it is 2 J plus 3 and minus GS. GS is 5.5857. If the last nucleon is proton, then it is this, which is mu n J 2 J plus 1 and 2 J here and minus 2.5857. Can write it J over J plus 1, J minus 1.2928. Then neutron. If the last nucleon is a neutron, GL is 0. So, this expression becomes mu z is equal to mu n J over 2 times J plus 1 and minus GS, right. So, plus 3.8260, that is all. This is J over J plus 1 and right 1.9130 mu n. So, all the 4 cases are now collected. This is for J equal to L plus half. This board, this portion is for J equal to L plus half here. Here this is for J equal to L plus half, and this is for J equal to L minus half. For L plus half you have proton, last nucleon proton, and last nucleon neutron, and similarly for L equal to half, J is equal to L minus half, you have for proton and you have for neutron. So, this is calculations, these are expressions calculated assuming that the magnetic moment of this whole nucleus is coming only because of this last unpaired nucleon. This is for odd A nuclei where either Z or N is odd. So, assuming this is that extreme single particle model, that entire property of the nucleus is determined by one single nucleon, which is the last one. So, assuming that these calculations have been made, if I write it as a plot J versus J, let me write it for first neutron. If that last particle is neutron, so if I collect all the magnetic moments of odd A nuclei with last particle as neutron, what should I get? This side if I write J, that last nucleon, what are the possible values of J for that in an odd A nucleus where Z is even, N is odd. So, there is a last unpaired particle neutron. We are looking for the possible J values of that nucleon. What are the possible J values? Any consider any odd nucleus, odd A nucleus with capital N odd, Z even. So, that last unpaired nucleon, unpaired particle, what are the possible values of J? 0? Is 0 possible? No, 0 is not possible. One single nucleon we are talking. For one single nucleon, L can be 0, 1, 2, it can be in S half state or P 3 half, P half, D 5 by 2, D 3 by 2, all those things you have seen. That J value is always 1 by 2 or 3 by 2 or 5 by 2 or 7 by 2, it has to be an half integer value, because it is one single nucleon. So, you have that spin quantum number half and orbital angular quantum number integer, and when these two couple L and S, it has to be half integer. So, the values are half, 3 half, 5 half, 7 half, 9 half, 11 half. In the shell model you had seen all those states. It is there on your screen also. Look at the screen. Those values at the rightmost thing, S half, what is that half? That is the value of J. This 3 by 2, that is the value of J. 5 by 2, 9 by 2, 7 by 2, these are the values of J. So, for one single fermion, J has to be half integer. Electron also, electron is also spin half particle. So, for one single electron, if L and S couple and give you J, that J has to be half integral, okay? And the minimum value is half. It will start with half, 3 by 2, 5 by 2 and so on. So, if you come to board, if you have this mu z and if you are trying to write all those mu z values, the J is not continuously changing. J will be half, J will be 3 by 2, J will be 5 by 2, J will be 7 by 2, 9 by 2, 11 by 2 and so on. And this side if I write mu z. So, neutron, two cases. First, this case, if J is L plus half, for example P 3 by 2, if that last nucleon is in P 3 by 2 state, 1 P 3 by 2 or 2 P 3 by 2, P 3 by 2. So, P means L is equal to 1. If L is equal to 1 and J is 3 by 2, so that is this case, that is this case. D 5 by 2, D 5 by 2 is this case. So, for such nuclei, if I collect all these things, mu z is just minus 1.9130 mu n, does not depend on j. So, all these magnetic moments should have some fixed values. So, it should be here, here, these are the these are the extreme single particle model prediction, right. It should be this much, minus 1.9130 mu n. So, it should be, if j is half, it should be this much, 3 by 2 this much, 5 by 2 this much, 7 by 2 this much, this. Whereas, if this last neutron is in the state where j is L minus half, like p half state or d 3 by 2 state, there j is L minus half, d 3 by 2, j is 3 by 2 and d means L is 2. So, j is L minus half. So, if the last nucleon happens to be on that this type of states, then it will be given by this j plus 1, j by j plus 1, 1.9130 and so on. So, you can put the value of j equal to half, and then you put a dot there on the graph, then put j equal to next 3 by 2 and so on, and you do that. So, you will have certain values. So, you will have some value here, it is not to the scale, the book you can see, it will be here and then it will be here and here and so on. It will be something like a okay, there is no meaning of intermediate points, but still you can join by straight lines like that. So, if you collect all the magnetic momenta of odd A nuclei where the last particle is neutron, it should be either here, 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 or here, 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 here. Now, when we collect the experimental data and plot here, what we find is there is a good spread. The measured values are less than this and more than this. So, it is in between. For j equal to half, for example, many of the particles have magnetic momenta here, somewhere here, and many of the particles have momenta somewhere here. In the book you will see the diagram, maybe I can show you like lecture. Similarly, for j equal to 3 half, those magnetic momenta experimental values if you collect, again you find that it is not exactly this, it is not exactly this, but somewhere in between, something of this sort. This is how everywhere, this is how everywhere. So, these calculations are not very good, right. If extreme single particle model was really the model, realistic model, then you should have magnetic moment either this one or this one. But what you find is, if you collect all those odd A experimental values, they are somewhere here. It is giving some kind of limit. It is not going beyond this line, it is not going beyond this line. These calculations were done by Schmidt, and so these lines are called Schmidt lines. Okay. So, the measured values fall between these two lines. So, these two lines, the extreme single particle model is giving some kind of a limit, upper limit, lower limit, but the values it is not that good. Similarly, if the second case you plot for protons, this was for neutrons, and for protons if you do a similar thing, for protons you do similar thing, the expressions now are to be taken from here and from here. So, this is j minus half plus 2 point this, and so you take expressions from here and there. So, if you put j equal to half for example, then it will be this much, and then you increase j by 1 unit and it will go up, and it's a linear function of j here, right. It's a linear function of j. So, j is equal to half will give you this value, and after that it will increase. So, it will start from this 2.7928, this will be 2.7928, and after that it will keep on increasing. So, you have a point here, you have a point here, then you have a point here, here and here and so on. Whereas, the other expression if you take from here, j is equal to 1 by 2 will make it negative. So, it will start below, but j equal to 3 by 2 will make it positive, and it is a little bit non-linear because of this j plus 1. So, it will not be on a line, it will be the first one may be somewhere here and the second one will go up and so on. So, you will have some kind of you can do it similar simple expressions, you can put the values, calculate it and nicely scale it 1 2 3 4 this side that side, and you can just plot how does it go. So, it will be some curve, not a straight line, but on a graph to the scale. If you plot, you find it. And here also the same thing, the experimental values are in between. Okay, experimental values are in between. So, the Schmidt lines give some kind of limit, but not the exact values. Then there are explanations. One is that perhaps this extreme single particle model itself is not the right description, and there could be more coupling between the so called pair neutrons or paired protons. It is not that all paired neutrons and protons are just sitting idle and only the last nucleon is contributing. So, that is questioning the single particle model itself. That is one possible way of looking at it. Another thing which can contribute that, all right, the particle model is okay, extreme single particle model is okay, but then the value of Gs for a neutron or for a proton when it is part of a nucleus could be different from the values that we have used for a free proton or a free neutron. Remember for electron this Gs is 2 or 2.0023. So, for a structureless particle it has to be 2 fermion, it has to be 2. Theory also tells that and experiments also tell that. Now, for proton it is 5.5857, for neutron it is minus 3 point and so on 8. This is because they have that charge structure inside. Okay. That is why neutron has a magnetic moment, otherwise why should neutron? Now, when this nucleon is a part of nucleus and it is surrounded by other quarks and other mesons and all those virtual particles and all that structure, okay, it is possible that the value of Gs is not the same when it is just one single nucleon, free single nucleon. So, empirically if you say that the value of Gs is reduced by say to 60% of its free value empirically, no theory for it. So, that these lines that you have drawn make it compressed 60% of the value, then the agreement will be little more better. So, if I take Gs at some 0.6 of the free Gs, then this line shifts here, and then it seems that okay, there are some points this side, some points this side, and it is going from in between. So, agreement is little better. So, maybe both the things are there. magnetic moment can also come from the so called paired particles, part of it, little bit of it, and part of it coming from this extra value of other value of different value of Gs. So, that is, so that means this single particle model, extreme single particle model is roughly it's fine, but the kind of success it has for deciding the spin parity of nuclei, and especially in grounded state, that kind of success is not met here. It's partially successful, right. So, that is about. Then you have a quadrupole moment, electric quadrupole moment. If the nucleus is spherical or any charge distribution is spherical, then there is no quadrupole moment, quadrupole moment is 0. But if the charge distribution is not spherically symmetric, then you have this quadrupole moment. From single particle model, and especially if you have a closed shell and then you have one extra nucleon, or from closed shell you have one less nucleus, so one whole state. So, for that one can make certain calculations that what non sphericity will be induced, and from there what should be the quadrupole moment. So, it turns out that you can make a calculations with this extreme single particle model, and the calculations give quadrupole moment which are much lower than the experimental values. Signs are okay, the plus minus sign, whether this quadrupole moment should be positive or negative, that comes out correctly, but the value is something like 10 times smaller than the observed value. So, in certain areas it has success, in certain areas it has partial success. Okay. Now, I will show you some excited states, and you will see what single particle model tells and what are the experimental values, and we will see the limitations or the need for other kinds of models. So, look at the screen now. I am giving you some excited states. So, look at the screen. What I am showing here are the measured energy levels of oxygen 17. So, you can see you have 8 protons and 9 neutrons, and the ground state is 5 by 2 plus. Next excited state is half plus, then you have half minus, then you have 5 by 2 minus, then 3 by 2 minus, and 3 by 2 plus. There are more, so just concentrate on these ones. The energy level diagrams according to the shell model is also there. You have 1s half, 3 p 3 by 2, then p half, then the third shell starts d 5 by 2 s half and d 3 by 2, then you will have 1f 7 by 2, next one, and so on. You have 8 protons. So, those 8 protons will just fill these first 2 states. So, proton and proton here, then 4 protons here and 2 protons here. So, this will close a measure shell, right. So, 2 plus 4 plus 2, that is measure shell closure here at 8, 8 is a magic number. So, this forms a closed shell. You have 9 neutrons, these 9 neutrons. So, 2 here and 4 here, and then 2 here, and the 9th one has to go here. So, the ground state spin parity is decided by this 9th neutron, and that is in d 5 by 2 state, and therefore, it should be 5 by 2 plus. So, that is 5 by 2 plus. We had discussed this example before also, but there are some extra energy levels for which I am discussing it again. This first excited state half plus, this one, this excited state, this is understood if I say that this neutron just goes in this level, right. So, from here it goes here. So, that is the excitation, and that is S half. S half means half plus. So, this is half plus. Now, the next one is half minus. How do I get this half minus? This is coming if I break this pair here, put this neutron here, and then the unpaired neutron is in this p half state, and p half will give you half minus. So, that is how this half minus is seen. So, see, it is a slight deviation from that extreme single particle model, which says that everything is decided only by that last unpaired nucleon. No. Now, breaking a pair needs energy, right. Making a pair saves energy, and breaking a pair needs energy. So, if I look at this half minus state, which is obtained by first breaking a pair and then taking this neutron up, and see the difference is more than 2 MeVs. Typically, breaking a pair takes about 2 MeV of energy or little less, depending on what nucleus it is. So, remember this energy difference here that you see, this energy difference is coming from two parts. One part breaking the pair here, and the other part is exciting from this energy level to that energy level. So, that is half minus, that is okay. Now, come to this phi by 2 minus, this state here, and work out how you can get a phi by 2 minus from this energy level. Phi by 2, you only have one phi by 2 on this diagram, that is d phi by 2, but then this will be phi by 2 plus d phi by 2 here, d phi by 2 here, which is the ground state in fact. If you go up, you will have 1 f 7 by 2, and above that, if you wish, what is there above this 7 by 2, that also you can see, it is p 3 by 2, then f phi by 2, right. That f phi by 2 can give you phi by 2 minus, but it is much higher. Your last nucleon was here in d phi by 2, and if you think this nucleon going here, it is much higher energies, and you need many more states before that. You should have a 7 by 2 minus, there are so many states, this energy is very high, this gap is very high, whereas the phi by 2 minus that you are getting in your level here is just close to this 1 by 2 minus, right, very close. So, looking for that phi by 2 minus beyond this thing somewhere here, that f phi by 2, that is not feasible. This neutron going to this state and giving me phi by 2 minus, that is not feasible. So, from there this phi by 2 is coming. See this 3 by 2 plus, you can see that 3 by 2 plus here, that is simple. This neutron coming here will give you this 3 by 2 plus, and this phi by 2 minus is much below that. So, do not think of this f phi by 2. So, from where I am getting this phi by 2 minus, right, there is a question. This is the ground state configuration, and I need that phi by 2 minus. So, that if you study it carefully, that can come, the only thing that I can see, phi by 2 minus at such a lower energy, lower means as compared to the f 7 by 2 and f 5 by 2 sitting at very high energies. This can come if this neutron goes here, this neutron goes here. So, you put this neutron here from here, and one of these neutrons break and come here. Okay. So, this neutron comes here. So, you have a neutron here and this has gone out. Now, you have 3 unpaired neutrons, one unpaired neutron in this p 3 by 2, no, p half, this is 1 p half. Okay. So, one neutron is here, another unpaired neutron is here in d phi by 2 and another neutron is here in s 1 by 2. So, you have 3 unpaired neutrons. So, you have J 1 is equal to what? P half. So, J 1 is equal to half and parity also, let us write parity also. So, half minus P half, correct? P means L equal to 1, parity negative. Then one neutron is here d phi by 2. So, J is phi by 2, J 2 is phi by 2 and parity is plus. And then you have third one sitting here S half, S half. So, you have J is half, J 3 is half and pi 3 is S is positive parity. So, when these 3 combine you can get negative parity, and these angular momentum when combine, this one and this one, you can get phi by 2, right. This half and half can combine to give you 1 and 0, and that combining with phi by 2 can give you phi by 2, can give other things also, but can give you phi by 2. So, this phi by 2 minus can be understood if you have this breaking of the pair and then combining things, right. All right. Now, let me show you something else. This, study these two things. This is calcium 41 and scandium 41. Calcium Z is equal to 20 and N is equal to 21, right. Z is equal to 20 is the shell closure, remember, and then you have this 1f 7 by 2 next one. So, this 21st neutron should go there. Should I show you the original diagram? This one, your shell closes here, this is 20. So, 20 protons, 20 neutrons will fill the major shell, and that last neutron will be here F 7 by 2, and then excitations you will have different energies. In scandium, N is equal to 20 and Z is equal to 21. So, the only difference between two is that last nucleon is proton in the case of scandium and neutron in the case of calcium. So, here the energy level diagram is similar. The ground state is 7 by 2 minus here, 7 by 2 minus here, and why it is 7 by 2 minus? This last nucleon is going in 1 f 7 by 2, right, and therefore, the ground state is 7 by 2 minus. Then excited states also you can see what are the excited states from the shell whatever diagram, and the first excited state is 3 by 2 minus, next one is 3 by 2 plus, and here also it is the same. That is all right. Why I am showing you that the values, see the separation here and see the separation here, and similarly this one is closer to 2 MeV and this is a little bit smaller than this 2 MeV. So, the values of energy, although the order is same, but the values of energies are different. Okay, it is the same, almost same 20 21 and 21 20, but proton energy levels and neutron energy levels are somewhat different. This is a middle weight nucleus. We had talked about this earlier. If you look at the potential well seen by this proton in the nucleus and neutron in the nucleus is slightly different because of Coulomb interaction. The potential, nuclear potential, single particle potential, that itself is slightly different because of Coulomb interaction. Neutron does not see that Coulomb part of the potential, whereas proton does. So, because of that you know how that potential changed, and therefore, energy levels change little bit. These things will be more prominent if you go for heavier nucleus, right. So, the neutron energy levels and proton energy levels in that energy level diagram are different. The difference is not very significant for light nuclei, but as you increase that capital A, you can see that the difference is more. Now, the next slide that I am showing is compare this 41 calcium with 43 calcium. 41 calcium is here, that is Z is equal to 20 and N is 21, the same diagram that you had in the previous slide. And this one calcium 43, so Z is 20 and N is 23. So, if I believe that extreme single particle model, there should be no difference, because the last unpaired nucleon is neutron in both cases, and that neutron is in F7/2 state, n equal to 23 or n equal to 21. So, all the 3 neutrons are in that F7/2 in this case 43 calcium, and that last one neutron is in F7/2. So, whatever excitation this that, if that out of those 3 neutrons, if 2 are paired and do not take part in nuclear properties, then they should be same. But you can see that there is a huge difference, right. There is a huge difference in the energy levels of calcium 41 and calcium 43. You have so many low energy states coming in. According to that shell model, extreme single particle shell model, let us see what you expect for these excited energies. So, remember here 3/2 minus and 3/2 plus. So, here is that last nucleon in case of calcium 41 and 3 in case of calcium 43. So, 3/2 minus is very clear, this goes here and it makes it 3/2 minus, right. What was next? That was 3/2 plus. That can you guess how can you get 3/2 plus? 1d 3/2. So, right. So, first excited state comes from this excitation, and for second excited state what you can have is that these out of these 4 neutrons which are here, break one pair, take it here, so that this gets paired and that one extra neutron is here which is 3/2 plus, right. So, this is fine, that is okay. If it is 1 neutron here, then also it is okay. If you have 3 neutrons here, then also it is okay. First excited state can come n going here and the second come by breaking this pair and making a pair here. But so many things, and look at the energy differences, but so many extra levels coming in at 43 calcium, all these things. This 3/2 level is at this height, little lower than 2. Before that you have 5/2 minus, 3/2 plus, 3/2 plus, this 3/2 plus, this 3/2 plus is more than 2 MeVs, it should be, because this 3/2 plus is coming by breaking a pair in d 5/2. Breaking the pair in d by, and breaking a pair needs about 2 MeV of energies. This 3/2 plus cannot come that way, it is much lower. Okay. So, from where all these things are coming? And the explanation is that the extreme single particle model is not working. In that F7/2, if you have 3 neutrons, then saying that these 2 have paired and only this is there, that is not working. Probably this pair is broken fine, but then there is a reconfiguration between these 3. So, all these 7/2 7 by 2, 7 by 2 are coupling inside, or maybe some coupling with someone else. So, that extreme single particle model is successful in many cases, especially in spin parity predictions, partially successful in the magnetic moments. Then it gives a justification of putting that asymmetry term in binding energy, why we divide by capital A and all that. These things are why you have more neutrons than proton in a heavy nucleus. So, many of the things could be understood using that extreme single particle model, but then we need something else also. This will not go too far to understand the nuclei, right. So, now next time what we will do, we will be combining features from this shell model and features from that liquid drop model that we used for semi empirical mass formula, and come out with something else which are normally called as collective models. Okay.